In this video, I'm going to take a look at a couple of well-known power series. You might remember when I started this whole concept of power series, I said that the primary reason we would be doing this would be allow us to find values. I talked about the idea that we have to use trig identities to find the sine of 75. How can I find the sine of 63.21 or the cosine of 126.7? Or how can I find e to the 3.21 power? And the idea is that we were taking these functions that are not polynomial functions, and we're writing a polynomial representation of the function. And the more terms you write out, the more accurate that representation will be. It's really, really easy for computers to extend these patterns out pretty far, generate values really quickly, and also in calculus, you'll learn there are actually ways to check the error involved. And so we can actually identify, if I want to go out to 5 decimal places of accuracy, you can actually calculate about how many terms you'd have to write out to accomplish that. And then, that's what number is generated on your calculator screen. So that's where we're going to be headed with this. It still may not be real obvious from this lesson, but we'll eventually get to that. All right, so there are a couple of well-known power series. They're developed using calculus, and something we'll obviously look at somewhere down the road. But anyway, there's some pretty well-known series here, and I'm going to look at 3 in particular. The e to the x function is really, really common in higher level math. And as a result, the series representation is pretty important. Obviously, you all have seen the sine and cosine functions are really important. They are also pretty easily represented using power series. So here is the e to the x power series. Very simple power series. All of these are going to involve factorials for a reason that's not going to be real apparent until you take later courses. But the e to the x function can be represented as 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and again extending out farther and farther and farther. And by the way, the pattern here, if you try to put this into a general term, notice we have x to the 0, x to the 1st, x to the 2nd, x to the 3rd. So we have an x to the n power here. Technically, this is 1 factorial, right? 1 factorial is equal to 1. Technically, this is 0 factorial. So you can view this term as x to the 0 over 0 factorial, and then you get 1. This is x to the 1st over 1 factorial, and so on. So when you're working these out, you may just want to write all of these terms, including those factorials. I have a tendency to kind of leave those out if I'm not careful, okay? So let's say that you wanted to get a decent decimal approximation of the value of e, for example. Most of you probably know e is about 2.718. If you wanted to do that, you're trying to find the value of e to the 1st power, okay? You can just substitute 1 in for your x value here, and you could write out a few terms. So that would be 1 plus x, but we're filling in 1 for x, plus x squared over 2 factorial. So you can do 1 squared over 2 factorial, plus, which of course is really just 1 over 2 factorial, plus 1 squared, 1 cubed over 3 factorial, 1 over 3 factorial, plus 1 to the 4th over 4 factorial, and so on. And the more of those terms you write out, the closer that result is going to get to the value of e to the 1st. So, you can substitute actual values in for x, and you can generate different numbers. If you wanted the value of e cubed, substitute 3 in for x in the series, and it would give you an approximation of e cubed. And again, if you write out 7 or 8 terms, you're going to get really, really close to the actual value. And the more you write, the progressively closer it's going to get, okay? We're also going to do a lot of work actually representing functions using these series. If you remember, we worked with the geometric series that ended up giving us rational functions, 1 over 1 minus x, functions of that form. And we could tweak them. So if I had 2 over 1 minus x, for example, you could say, oh, well, that's just the geometric series multiplied by 2, and you just multiply all the terms by 2, and you have your new series. It's kind of the same sort of thing here. So, for example, 5 times e to the x, I gotta just take the e to the x series, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on, out to infinity. I could just take that whole series, e to the x, and multiply it by 5, okay? And that'll give me 5 plus 5x plus 5x squared over 2 factorial. And you might want to work out your factorials. 2 factorial is 4, plus 5x cubed over 3 factorial, which is 6, and so on. And you can write out a whole bunch of terms there, and if you graphed it, at least for values near 0, it would look very close to the function g of x equals 5 e to the x. If you wanted to write the general term, the regular term is x to the n over n factorial. Each of the terms got multiplied by 5, so we could say if you go out infinitely far, the nth term would be 5 times x to the n over n factorial, and that's also what you could use in your sigma notation if you set it up with a sigma, okay? So that would be the series representation for this function, okay? So you can just take the function itself and you can multiply by something. If I wanted to do something like g of x is equal to x times e to the x, okay? Same kind of thing. I'll take the e to the x function, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on, out to infinity. And that's the e to the x function. And I'll just multiply the whole thing by x. And that's going to distribute through to each of the terms going out to infinity, and that'll give me x plus x squared plus x cubed over 2 factorial plus x to the 4th over 3 factorial, and so on. And if you notice, the only thing that changed from this series to this series is each of the x's has a power that's 1 greater. So you could just basically add 1 to your exponent there. Your general term would be x to the n plus 1 over n factorial. And then when n is equal to 0, you'll get an x to the first here over 1. When x is equal to 1, you'll get an x squared over 1 factorial. When x is equal to 2, you'll get an x cubed over 2 factorial, and so on. That's how you could write that series, okay? And then there's the second thing that could happen, which is they could change the input. So for example, if I wanted to do e to the 2x, this is e to the x, and so we see x in each of these positions, okay? What's going to change here is this would be e to the 2x. So anywhere you see an x, you would fill in a 2, okay, because your input has been changed. So you've got to change your input in the series to match whatever the input is in the original function you're given, okay? So the basic setup is that it is 1 plus the input over 1 factorial, which is 1, plus the input squared over 2 factorial, plus the input cubed over 3 factorial, and so on. Only thing that's changing here is the input is now 2x. So you'll have 1 plus 2x, and then you'll have 2x squared over 2 factorial, and you'll have 2x cubed over 3 factorial, and that pattern will continue, okay? And again, you could simplify each of these down. A lot of times you're going to get cancellations and things, and it'll kind of muddle the process, and it may be tough to see what's happening with your factorials and that sort of thing. So a lot of times I go back to the general term, okay? The nth term of this was x to the n over n factorial, okay? The input to the n power over n factorial. Instead of putting in an x and having x to the n over n factorial, I'm putting in a 2x. So the general term would be 2x to the n over 2 factorial. And you could write that as 2 to the n times x to the n over n factorial. You could do something like that if you wanted to. Anyway, just following this basic pattern, it would look something like this. And again, you could simplify this down. So this is going to be 1 plus 2x plus, that'd be 4x squared divided by 2, which is going to be 2x squared. And then this is going to be 8x cubed. Oh, sorry, that shouldn't be cubed there, it should be 2x. That'd be 8x cubed divided by 6, which would be 4/3 x cubed. and then so on. Anyway, you'll see sometimes when you simplify it because of cancellation, it kind of makes it unclear. So I think in this version, it's very tough to look at this and try to figure out what the general term would be. So, you know, it just kind of varies. Let's say I want to do something like h of x is equal to, let's do 2e to the x squared, okay? So two things happening. My function's being multiplied by 2, okay? So maybe we want to have the whole function being multiplied by 2 out in front. And then instead of having an x as my input, I have an x squared as my input. So my series is going to be 1 plus the input squared over 2 factorial plus the input cubed over 3 factorial and so on. But my input here is going to be x squared. So it's going to be x squared here. Oops. It's going to be x squared here, sorry. X squared. We'll have x squared squared, which I have here. We'll have x squared as my input cubed, and so on. And again, you can multiply this whole thing out. You're going to have 2 times 1 plus x squared plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial, and so on. Each of these terms would be multiplied by 2. So you could also write this as 2 plus 2x squared plus 2x to the 4th over 2 factorial plus 2x to the 6th over 3 factorial. And if you put all that together, your general term, you'd be multiplying by 2. Your exponents are increasing by 2 each time, but again, you can just substitute into the general term here. You've got a 2 out in front. It's going to be an x squared raised to the n power, and then you're dividing by n factorial. And so you might write that as x to the 2n power to simplify it, and you should be able to see that it'll go along with what you had before. So when x is 0, when n is 0, this will be x to the 0, that'll be 0 factorial. You'll just get 2, which is what you would get when you multiply there. Next term, you want to get a 2x squared. When n is 1, you'll get x squared, you'll get a 1, you'll get that. You want to get a 2x to the 4th over 2 factorial when n is equal to 2, okay? And if n is 2, you'll get x to the 4th, 2 factorial, and you can see that it kind of works out. So that would be your general term there. If you were doing a sigma notation, you could basically say this is the sum from n equals 0 to infinity of this, and that would generate the function y equals 2e to the x squared. Okay, I think I'm going to come back in a different video and look at a couple of the sine and cosine functions. That's coming up next.